Okay, everyone. Hello, my name is Hubert Baniecki, and I'm here to present our work on interactive sequential analysis of a model and how maybe it improves the performance of human decision-making. So this was done in collaboration with Dariusz Parzyk and Przemysław Biecek from Warsaw University of Technology. So I'm actually a PhD student in computer science here at the University of Warsaw, and I'm mainly working on explainable machine learning. Don't ask me why this presentation is in the track of AutoML, because I don't know. And also I'm working on applications of ML in biomedicine. So this is how I see myself, and this is also how Google Scholar sees me. So these are my collaborators. So yeah, I have an opportunity to work with physicians, medical doctors, bioinformaticians, and other people from our lab. And yeah, while preparing this presentation, actually what I did, after finishing my slides, I took the first part of the last slide and put it at the beginning. So this is what we should expect. Actually, the first conclusion from this talk will be that evaluating model explanation is quite challenging. That's it, okay. And so there are several ways to evaluate explanations. We have some measures and also software that evaluate that implement those measures to kind of evaluate explanations. Lately on NeurIPS also there were published some benchmarks for XAI and even ladder boards, like in NLP. Now we have ladder boards for model explanations. But this talk will consider kind of the human side of the evaluation of explanation process and how it relates to kind of humans. So these are kind of my two go-to examples of why we really need explainable machine learning, explainability in general. So first one is kind of from more business side. We know that models deployed in real applications, for example in banks, can be biased, and maybe we can use explanations to find out this bias and kind of upgrade our model to account for it. But also really recently there was published a big survey of models that were kind of deployed during the COVID pandemic, and kind of the main conclusion of the whole process was that none of the models identified, there were like 100 papers screened, are actually of potential clinical use due to many biases, and maybe explanations can help us to overcome this issue. So we explain black box machine learning for various reasons. Some might want to validate your model, kind of debug the predictions, see if the prediction maybe is wrong due to explanation giving like not unintuitive estimation. We also use our explanations for explanatory model analysis in a scientific insight, for scientific insight. So this is a process where someone creates a model and then tries to explain it to draw some conclusions about the correlation that are apparent in their data. And also we can improve our models. So this talk will focus on this first part of validation and debugging. And what we wanted to propose in our paper, this talk is based on our paper, the Grammar of Interactive Explanatory Model Analysis, which is available on arXiv, is kind of a second phase, a second generation of explanation. So first there were kind of black box machine learning models. We don't know really how they work. Your SVMs, your neural networks, we want to interpret their predictions. Then it occurred that we have like a dozen of methods for explaining those models published already, and each of them shows kind of one side of this black box model. And maybe it would be a good idea to compare many different explanations next to each other and draw conclusions from multiple explanations, because looking only at one side of the box might be misleading, or we might not understand the whole process here. So this is kind of the one way that we can kind of categorize the many explanations for here actually tabular data that we know, and what are the edges are kind of which explanation benefits from showing it next to other explanation. Of course, it's only our proposition, and other researchers propose other kind of combination of such explanations. And maybe what's crucial here in this process is that we have our usual local explanations, so they work on one observation from the data, one prediction. We also have kind of global explanations that look how the model behaves in general. But also what is crucially overlooked is the data. And many people kind of explain their models, but they actually don't pay attention to the data. And since explanations are very often estimated from the data, it's really, really important to look at the distributions of data when interpreting models. So yeah, this is kind of the highlight also, that a few of explanations benefit from showing data distributions, for example. Or, of course, also pairwise correlations. We know that a huge limitation of nowadays explanations is the fact that they often assume that variables are independent of each other. So if you have kind of the correlation heat map of our variables, then we know maybe how to interpret our explanations. Yep, so in this work we show a few ideas on a few use cases, how we can kind of join this explanation each other and maybe draw more meaningful and useful conclusions. And there are some keywords that are attached to this process. So yeah, first of all, this is a process. Explaining a model is a process. It's not just looking at one visualization and saying, yeah, this feature is important. Maybe let's try to compare 3 different visualizations of feature importance. Also, since it's a process, it's kind of interactive. We first create a plot, we draw some conclusions. Maybe we then need to create another plot. This is how you also improve your models in general when you work kind of in a usual setting. And what comes out of this process are kind of these sequences of explanations that we can use to interpret our machine learning model. And this work actually started, okay, we have this theoretical framework, how to use it. So there is actually software proposed by us that you can use to kind of analyze your model in an interactive and sequential manner. Here there should be an animation, but this is actually a PDF slide. I couldn't port the PowerPoint here. But this animation shows software, kind of a dashboard that we implemented that you can use to interactively explain your model. And this work was actually presented at MLIMPL last time we were on site in 2019, and I was really happy to have a poster with it. But now the question is how to evaluate if this sequence of explanation brings any insight, right, to our approach, like how to evaluate this whole process. So one idea would be to actually sit with someone who wants to analyze the model in this dashboard, in this interactive dashboard, and ask him questions about his idea of interpreting the model. But this would look more like, I don't know, product development. We would ask him what features he would like to know about, I mean, what features he would like to be added to this software. So we kind of wanted to create some controlled experiment with humans to answer the question of if this sequential analysis of a model brings any value. And this is how we came around to create a user study, which is a about 35-minute questionnaire that each of you should be able to kind of finish. And our goal was to see if this interactive and sequential analysis of a model brings value to explaining block-based machine learning. So I started my presentation by saying that there are these 2 poles, that there are these measures that we can use to quantify our explanations, but also there is human on the other side. So we don't want to kind of analyze if the explanations are kind of faithful to the model. We care more about if they bring any value. What is this value? So our research question we want to answer is kind of showing and interpreting those multiple explanations in sequences, increase the usefulness of explanations. What can be useful in explanation? They kind of increase the accuracy and confidence of human decision making. So human has to make some decision based on the model, based on its explanation, and we want to see if we show him a sequence of explanations, he will kind of better answer some questions. And our target group in this user study were actually model developers, not domain experts. It is hard to evaluate explanations on a large-scale group of domain experts. For example, in our use case, which is actually a medical case study, we had access to 3 medical doctors, physicians. Okay, we can kind of put them through a questionnaire, but then taking conclusions from asking 3 people might be hard. We had considerably more higher access to people which are from the target group, which is model developers. So this is what we aim for. So our case study is based on a real acute kidney injury prediction task from one of the Krakow hospitals. So there is kind of simple in a sense of correlation based in the data task of classifying whether someone will obtain acute kidney injury during a hospital stay based on some medical biomarkers. And there are two really important features in this data which are positively correlated with the target. So there's no really much that we don't really need much medical insight into interpreting this predictive task. And we trained a random forest model and now created a questionnaire, and the task for the users was to answer if a given prediction for a given patient is actually accurate or not. So we might think about a case that there is a patient in a hospital. The model predicts that he will or she will get this acute kidney injury, and now the model developer comes and looks at the explanations and is tasked with kind of making a decision if this prediction is wrong or not. Can it be done? This is the question. So what the user would see after, of course, the introductory course to the whole case study would be kind of one explanation for a given patient. This is actually a breakdown of its prediction. So here is the prediction value. So actually a probability of gaining this acute kidney injury is like 0.045. And these are the variable attributions for a given patient. And now a user has to make a choice. So the question is the class predicted by the model for this prediction accurate? And the user would choose definitely yes, rather yes, definitely no, or rather no, or I don't know really. And our first hypothesis was that looking only at such explanation, the user won't really know if this is an accurate prediction or not. This is why we wanted to see if adding more explanations would change his answer. So after kind of putting your answer here and clicking next, what you would be shown with are two explanations, and the same question is answered. So is the class predicted by the model for this patient accurate? And now you have like more information to make your decision if this prediction is accurate or not. So here we see a what-if plot for the most important variable, and maybe this is kind of an indication of how confident the model is about the importance of this most important variable. So then after putting your answer and clicking next, what the user would see is actually 4 explanations. You need to believe me that here are 4 explanations. And the same question would be asked. So now the user has like full information given to him, and he can kind of answer the same question. And this would be done for 12 patient cases. So there would be 12 patients in the hospital. The user would know that about 6 of them are accurate, 6 of them are wrong. And now the question is to kind of see if he can find out which one is which. And the result would look something like this. Here in the rows we have cases, patient cases. There was one test case, but here is case 1, question 1, case 2, question 2, case 1, sorry, question 2, and case 1, question 3. And in columns we have our respondents. So there were actually 46 respondents, but only 31 finished the whole questionnaire. And from such data, we can't really deduce anything, so let's maybe try to aggregate the answers. Here are some aggregations. So this plot shows kind of the aggregated answer for 6 patients which had the correct answer no. So the model was actually wrong in these cases, and we wanted to see if people would kind of be able to distinguish that these are wrong predictions based on the explanations. So here I kind of highlighted the most kind of obvious case. This is the case 6, so patient 6. And now here we see that after showing only one explanation for this prediction, most people kind of said that this is probably a proper prediction. But after adding more explanations, more people kind of changed their opinion on the process. And after adding even more explanations, even more people changed their decision about the process. There are also other cases, like here, patient case 12 was actually really hard to distinguish if it's correctly predicted or not. And kind of we see unambiguous behavior where first many people were kind of sure that this is a proper prediction. Then after adding another explanation in this sequence, many people changed their mind, so they changed their answer. But then actually after adding even more explanation, they changed their mind to another answer, which is no. And this is kind of connected with the cognitive load, that not always providing more information to the person gives them a kind of easier time at interpreting the results. So this is what we did for the aggregation, what we did for all the patients, and now we want to aggregate it even more. And this is how I come to the final result of the user study. So here we first, of course, got these accuracies for each patient case. So this is kind of the accuracy, which would be the frequency of proper answer given by 30 respondents. And then its variance would be based on the aggregation over 12 patient cases. So this number is kind of the mean of the accuracy, and this standard deviation actually is based on aggregation by 12 patient cases. And we see that in question 1, kind of the accuracy of people finding out if the model predicted accurately or not is random. The accuracy is 50%, about 50%. But actually, during question 3, more and more people interpret the results properly and say that this actually might be a wrong prediction if this is the case. And this kind of difference can be, of course, somehow measured. There are some statistical tests without checking the assumptions, but we can say that this is significant or not. What is really interesting is also that showing more explanation to the user. So here in question 1, we have only 1 explanation. In question 3, we had 4 explanations. Kind of the proportion of people saying that they don't really know decreases. And this also was kind of nice to see in our user study. There were also more questions in this questionnaire. So people were, I don't want to go into details because I don't have so much time, but people were also shown global explanations, and they could use it to kind of make their inference. And like 20%, in 20% cases, people actually said that these global explanations were really crucial to make their decision. So maybe kind of showing multiple explanations is kind of beneficial. And a part of kind of quantitative analysis, we also did qualitative analysis, which you can read about in our paper. And I kind of highlighted the possible drawbacks of our approach here that the users indicated in the open question. So many people said that actually showing too many explanations generates the risk of cognitive load, which is kind of consistent with the literature in psychology. But also that really you should have clear instructions on how to interpret the plots to kind of make them a meaningful decision. So yeah, this is how we arrive at the end of this talk. And first conclusion doesn't really change. We had really a lot of challenges in creating this user study, but we arrived at, to our surprise, a positive kind of answer. And the second conclusion is that we think our study indicates that an interactive sequential analysis of a model has a potential, because this is only one case scenario, to increase this accuracy and confidence of human decision making. Yep, if you have any details, you can see the paper on preprint or ask a question now.
Thank you very much. Let's give Hubert a round of applause.